Imagine wandering through a maze, trying every corridor, backing out of dead ends, and slowly figuring out the route. Now imagine something that can solve that same maze more efficiently than you despite having no neurons, no brain, and no nervous system at all. This is Physarum polycephalum, a plasmodial slime mold. It's a single multinucleate cell, essentially one giant cytoplasmic network containing thousands of nuclei. Even though it lacks any neural architecture, it displays complex adaptive behaviors that resemble problem solving, spatial computation, and environmental inference. In classic experiments by Nakagaki and colleagues, researchers distributed pieces of Physarum throughout a maze laid on an agar plate, then placed nutrient-containing blocks at the two target points in the maze being the start and the goal. At first, the plasmodium spreads out, extending a network of tubes that explores all possible paths throughout the maze. Over time, two branches that do not efficiently carry nutrient flow retract, while those carrying higher flow become reinforced and thicker. Eventually, the slime mold leaves behind a single efficient path connecting the two nutrient sources, effectively computing the shortest route throughout the maze. This process parallels how computers solve optimization problems. In graph theory, algorithms like Dijkstra's find the shortest path by evaluating and updating the weight of different edges. Slime molds do something similar, but physically. Rhythmic oscillations pump cytoplasm through their tubes. Tubes with high conductance carry more flow, triggering biochemical reinforcement, whereas tubes with low conductance retract. This feedback loop effectively performs a continuous parallel update of edge weights, allowing the organism to approximate shortest path and minimal network solutions through its own morphology. One of the most striking demonstrations of this was in 2010 when scientists replicated the geography of Tokyo by placing oat flakes where the city's major stations are located. Over several hours, the slime mold produced a transport network with efficiency and resilience remarkably similar to the actual Tokyo rail system. A unicellular organism arrived at a solution comparable to human-designed infrastructure. This forces us to broaden our definition of intelligence. Cognitive science usually focuses on computation done by neurons and synapses, but Physarum shows that intelligent-like behavior can arise through embodied computation, where an organism's materials, flows, and geometry do the information processing. It stores memory in the shape of its own network and computes through distributed analog-like updates. So when we think about computation, we shouldn't picture only silicon chips or artificial neural networks, but also a bright yellow slime mold that solves problems by reconfiguring itself. Sometimes intelligence doesn't require a brain, only the ability to adapt through self-organized computation. And as we enter an era shaped by AI, this reminds us to look beyond familiar architectures and imagine forms of computation and intelligence we haven't yet built.